Okay. And lastly, the enzyme, I probably won't ask you any questions, but I won't ask you any questions about this. An enzyme called nucleoside diphosphate kinase catalyzes the conversion of ATP to GTP, the reversible reaction between ATP and GTP. And the key idea here is that no energy is lost, no energy is gained in this transfer. It doesn't favor one side or the other, but whether it will basically equalize based on what's necessary. Next reaction. Almost done. 3 more. Oxidation succinate. Yeah. The oxidation reaction of succinate is catalyzed by succinate dehydrogenase. That's what's going to be generated. Right, we're losing electrons, so we are going to generate NADH or FADH2. Succinate dehydrogenase is a flavoprotein. And you see this flavin between. Flavin between means it needs a special type of electron carrier. FAD. And this catalyzes the oxidation of succinates. A few things about this reaction. It is stereospecific. And the product is virtually all trans fumarate. For your exam, you should be able to calculate oxidation states, right? You like this. Oxidation state. What is the change of oxidation state? Clearly, nothing's happening to this carbon. Nothing's happening to this carbon, but these two carbons have changed. What's the change in oxidation state? What would the oxidation state of this carbon be? What would the? Oh, you're right. Huh. -2, what would the oxidation state of this carbon be? 1. What's the oxidation state of this carbon? 2. Oxidation state of this carbon? 1. So we're going from -2 to -1, -2 to -1. How many electrons do I lose or gain? Lose how many? 2, right? Loss of 2 electrons from 2-electron oxidation. Succinate. We also call this a 2-electron reduction of what? Fumarate is going backwards. However, the oxidation going this way is also paired with the reduction of FAD. A few things that are unique about this reaction. FAD is an electron carrier in this enzyme complex that is covalently bound. FAD is an electron carrier, yes. It is covalently bound to this enzyme. That's kind of weird. It's covalently bound to the enzyme. So how in the world does it convert to FADH and then take electrons into the electron transport chain? FADH. Shuttles the electrons directly to membrane-bound coenzyme A or coenzyme Q in the electron transport chain. So it's coenzyme Q. And we'll get to this in more detail when we talk about electron transport chain. Not to do this phosphorylation in the last example. This oxidizes FADH back to FAD. Coenzyme Q. So FAD is oxidized. FADH is oxidized back to FAD. Coenzyme Q is reduced. UQH2. This is how FADH is introduced into the electron transport chain. Step 7, another stereospecific step. Fumarate is hydrated to L malate, D malate. So cis fumarate is hydrated to, just said cis, trans fumarate is hydrated to L malate. Analyze by fumarates. Stereospecific in both directions. Reversible step, it's stereospecific in both directions. I'm not even going to draw an intermediate. You can find, you'll find two proposed mechanisms. Mechanisms aren't really known for this enzyme. You can find two proposed mechanisms in your text. I think you'll find only one of them in the linear text. One of them, the two mechanisms will talk about. Your intermediate step either can go through a carbocation intermediate or a carbanic ion intermediate. But again, they're both close. This is stereospecific, meaning cis butyrate will not go, D-malate will not go in the opposite direction. Both of those can be used as suicide inhibitors. They're suicide inhibitors. They're not reversible, right? Suicide inhibitors are not reversible. Giving it up. 10? 9. Again, your textbook talks about some proposed mechanisms. Last step, then we're going to go back and we're going to review some stuff about glycolysis and the PCA cycle, and then we're going to do like a thought experiment. See something today that will be understandable. For sure. I think both of your textbooks talk about to some degree. The Biochem textbook talks about a bigger degree. But I gave you a bunch of homework problems talking about isotopic labeling, radioactive elements. It's kind of a cool experiment. So we're going to talk about how that works. Sure. Oxidation of malate, oxaloacetate. This is catalyzed L-malate dehydrogenase. L-malate. It's a reversible reaction, so it's not a regulation step. Here's the carbon and malate is it. So is it a conversion of L-malate? Enzyme L-malate dehydrogenase. This is how many electron oxidation? How many? Oxidation state of this carbon doesn't change, this carbon doesn't change, this carbon doesn't change, this carbon does change. What's my oxidation state here? 0. What's my oxidation state here? 2 plus 2. A loss of 2 electrons, so this is a 2 electron oxidation. I get it. 2 electron oxidation, 2 electron oxidation, 2 electron oxidation. It's not enough information. You need to be able to count redox states. You need to be able to count oxidation states. Lastly, I will tell you what is unique about this enzyme. Here's malate. So I was drawing these reaction arrows. under reaction arrows under standard state conditions. What do I mean when I say standard state conditions? In a test tube. That's a good answer. In a test tube. Those are standard state conditions, right? Standard state conditions, 1 molar concentrations of everything, right? 1 molar concentrations of everything. Room temp. pH of 7, right? In a test tube, what would this look like in a test tube? In a test tube, it would look like MDH is not doing anything. It would look like this enzyme doesn't do anything. Why? Because this enzyme favors a specific direction. It favors a specific direction. So under standard state conditions in a test tube, this is what we would see. However, this is not what happens. Why? Product what? Removal. Product removal. Product removal. Removal of product. Oxaloacetate is being pulled in a million different directions. It's going to be within reagent in many different pathways. Product removal. There is virtually no oxaloacetate hanging around. Okay. Let's go ahead and do it. Isotopic labeling. You may see this in some textbook. I don't know what the Biochem textbook stuff. You may see it talked about as a radioactive labeling. It is a way to label specific chemicals with various isotopes that we can track. So a lot of times you'll ask in a mechanism, how do you know this is happening? How do you know at this step this is the carbon? How do you know it's not this carbon? Or how do you know it's not this? How do you know it's this? A frequent test, a frequent experiment that's used often in probing mechanisms are experiments that include isotopic labeling. Label a specific carbon, label a specific phosphorus, and see how it moves. See how it moves. So, let's take acetyl CoA. You could do few experiments. You could literally label whatever you wanted to. Not whatever you wanted to. We all talked about exchangeable protons. This is a phrase you remember from organic. Exchangeable protons, yes or no? You may have not. It depends on who your professor is and what they like to talk about. If the professor did a lot of NMR, they probably talked about exchangeable protons. Didn't do a lot of NMR, they probably didn't talk about exchangeable protons. Some protons will exchange in solution, specifically OHs. You can't radioactively label an OH group with hydrogen at least. Why? Because that hydrogen is going to exchange with all the other hydrogens in solution. So if you label it with deuterium, guess what it's going to do? It's going to drop off. That water is going to pick up that deuterium and it's going to hand back a hydrogen. So you lose your isotopic label by solution if you label things that are, if you label hydrogens specifically. You can label a hydrogen here and it's not exchangeable, so that it would stick in some places. Okay, so let's say we are going to radioactively label this carbon. We're going to radioactively label this carbon with a different isotope, and then we'll be able to track it. So if we go back to step 1, all the way back to step 1, we radioactively label acetyl CoA. We're going to track it through this entire process. We're going to radioactively label here. We have a radioactively labeled carbon. We are going to track it through the process and see if we can determine if we ever lose information or if we ever lose that carbon entirely. Do we ever lose that information? Because some of these carbons are ejected as CO2, right? So is this carbon going to be ejected as CO2? Maybe, maybe not. We'll find out. Which step would it be ejected as CO2? So this carbon, after step 1, I do not lose my label, right? formation of citrate. We combine these two. This carbon is now so we have not lost our label. We've been able to track our carbon. Our next step, this is where it gets kind of weird. Which carbon is that? It's actually this carbon. It's not this carbon, it's this carbon. On this step, do I lose my isotopic label? Does anything change about that carbon? No, this one's easy to track. Still didn't lose that carbon. And yes, it did matter which carbon it was. It's not this carbon. Although it may look similar here, it's not similar, right? To this one. Citrate carbon. Our next step. It may take you a minute to identify, well, what carbon? Oh, it's this carbon. Right? This carbon. It's a carbon not near my CO2 group. Right? Not near my CO2 group, and it's not near this OH, which this one's near the OH. That carbon. Okay. Here, do we lose our label? No, right? We don't do anything else. We don't lose our label. So there's three steps, and we've been able to track this isotopic label carbon through all of our first three steps. Fourth step, we didn't write out a mechanism. Fourth step, I'll go ahead and tell you, we don't lose the label on your fourth step either. You can go back and look at our pyruvate dehydrogenase. I don't think we can do it. Anyway, we don't lose the label. Fifth step. We haven't lost the label on our fourth step. What happens on our fifth step? Reactive to product. A lot of textbooks, if you look at a lot of experiments, there's some debate on, do you lose your label here? Yes. Do you lose your label? You really don't, right? But you could kind of argue that you do. Why? You lose CoA, sure, but why could you argue that? I could say no, I didn't lose because I drew it this way. How could you argue and say, well, you did kind of lose your label? Now, how do you know which end it's on, right? It's symmetric. How do you know which end it's on? How do you know that it's this end, and how do you not know it's this end? So some textbooks may say, yes, you do lose your label. I don't know. I would say you don't. In actuality, it doesn't matter if you lose your label, if you don't lose your label here. Why? Because if you do lose your label, let's say we didn't know if it was this, or we didn't know if it was this. Let's say we lost our label and we don't know which carbon it is. Well, guess what? We still don't know which carbon it is, right? If we lost our label and we didn't know which carbon it was, we wouldn't know at this step. If we didn't lose our label, we would still lose it at this point, regardless, right? We don't know which carbon it is at this point. So really, you could argue reaction 5 or reaction 6 is the single step in which you lose your label. You end up with the same mixture on reaction 6, regardless. Is that carbon? There's this label here, is this label here. If you're tracking it the whole time, yes, it's in both places. We have a mixture. At this point, we lose our label. How much of it did we lose? You've lost the ability to identify which carbon is labeled, right? At this point, they are both labeled. We're following the same reaction, and at this point, they are both labeled. So we have a label here, we have a label here. Where's my label in L malate? Both, right? Again, both. It's still a mixture, 50-50 mixture. So I could say this is one, this is one. So I still have a mixture of labels, right? Still have a mixture of labels. Reaction 8. So we're through reaction 7, and we have not lost our label, correct? We've not lost our label. Reaction 8. CO2. Have we lost our label? No. we lose our label on this last step? No. Where's my label? Still a mixture, right? Still a mixture. Still 1/2 this part, still about 1/2 this part, right? So I've lost certainty, but I haven't lost my label. It's still there. What happens on the second turn of the TCA cycle? Let's go back. On the second turn of the TCA cycle, so now this is oxaloacetate, right? Oxaloacetate. So on the second turn of the TCA cycle, where is my radioactive label? My radioactive label, for my initial radioactive label is half here, half here. That's what we just drew. With me or lost me? Or Rick, you look like you lost me.
No.
You good? Okay. So we still have our label. We know half of it's here, half of it's here. Do we lose that label on this next step? No. Still have half, right? Didn't lose our label on the first step of our second turn of the TCA cycle. Second step of the second turn of the TCA cycle. Where's my label? My label is here. My label is here, right? I'm tracking my radioactive isotope label. Still don't lose it on my second cycle, right? Lose any information, I don't lose anything. Third cycle, my radioactive isotope is here, my radioactive isotope is here. What happens on reaction 3 of the second turn? You lose one of the CO2s, right? So you lose half of the label is lost as CO2 on the second turn of your third step. Second turn, third step, half of your label is lost as CO2. I still have some radioactively labeled. Right. So I have some radioactive label. Half of that gets lost to CO2 on the second turn of the third step. Third step. Well, we didn't draw this out. At this step, oh my goodness. At this step, we lose the rest of our label. Why do we lose the rest of our label? Because our isotopically labeled group from here, right? C-O, this is my CO2 group that is isotopically labeled, and I just lost it. Does that make sense? You have substitution of CoA, right? So I have an isotopically labeled group here from step 3, right? You didn't write reaction step 4, but what step 4 does is it replaces this CO2 group with a CoA, right? It replaces this CO2 group. So this reaction has a loss of CO2. So the other 50% of this label is lost as CO2. Yes, it would have been easier to see if we got a reaction. But if you go back to pyruvate on page 62, if you go back to pyruvate, you'll see on the first step right here, we lose CO2. That's the same thing that's happening. We're losing that CO2 on step 4. So, being able to track the progress of CO2 is something you should be able to, an isotopic label is something you should be able to do. I ask you to do it in your homework. There are a few questions talking about radioactive labels. If this radioactive label is introduced, how would that affect? Where will you see it? Where will you lose it? It's a good way to know reaction mechanisms. It's a good way to test that you know reaction mechanisms. What happens if I add inorganic
there's only one step that incorporates inorganic phosphate, right? In both glycolysis and GCA, only one step that adds inorganic phosphate. So if I add a radioactively labeled phosphate group, where would you see that? You would see it in this certain steps, and you would see it in these products, and where would you lose it? What's that?
Can you say again where it's
The first 50%, yes, this is the remaining is lost, right? So yes, not 50% of the 50%. It's just the remainder of what we had. So half of it's lost as CO2 at step 3. The rest of it, the remaining 50%, is lost in step 4. So that's where we lose our 2 CO2 groups. And those are the 2 CO2 groups that held the rest of that held the that much labor. Okay, some other things I wanted to. Oh my goodness, man, I have a few minutes. No regulatory steps. Again, no regulatory steps. You should. Both textbooks have really nice figures showing regulatory steps at each step of glycolysis. I think I gave you a figure out of the literature text, not the Biochem text. It was really nice. There is another one. There's a nice figure about the TCA cycle. There are figures in the literature text as well that show a nice breakdown step by step, which steps are regulation steps, what affects regulation at each step. You'll notice that in general, these things don't change, right? In general, these things don't change, and the questions that are going to be asked aren't specific. What is the one regulator for this step? You probably won't see that a lot, unless it's important. Like step 3 of glycolysis, there's one regulator that's really, really unique. You remember what it is? Step 3 of glycolysis has one regulator that is pretty unique. Citrate. Why is that unique? Yeah, it actually connects glycolysis to TCA. It's a signal in TCA, right? An intermediate step in TCA that can actually communicate with glycolysis. That's unique. And those are the types of things you need to know. I don't want you to know which one binds the AMP, which one binds the ATP. It doesn't matter, right? Things that the idea you need to have is that signals, cellular signals that tell us we don't have enough energy are usually positive activators. Cellular signals that tell us we have enough energy are usually negative allosteric inactivators, right? Or inhibitors. Knowing that generic information is great. I don't care that you know this one binds specifically to ADP or this one binds specifically to AMP. If you want to know that, if you want to be tested on that, take that rate. I promise you'll be tested on that. Knowing those general ideas, those general concepts is great here. However, you should know the unique ones. Enzymes that feed your product inhibition, that's unique. Specifically, like step 3, that's really unique. You have one pathway talking to another pathway. That's cool, it's unique. You should know those things. I think that's it. Right? Just kidding. My son's been playing basketball. On Wednesday, we will meet on Wednesday. On Wednesday, we shall meet, and we will start. We'll have 2 days before your next exam, right? 2 classes before your next exam. Wednesday, we will start talking about pentose phosphate pathway. On Monday, we will finish pentose phosphate pathway. If you want to ask me questions about the exam before Thanksgiving, that's fine. I'll give you 5, 10, 15 minutes at the end of class, or you can ask me questions on what do we need this, what do we need that. We'll do that. 2 more classes before your exam. We're going to be talking about pentose phosphate pathway. We will briefly, and when I mean briefly, I mean 10 minutes, talk about gluconeogenesis and glycogen metabolism. That is something you will cover in section in Biochem 2. However, especially for those of you taking MCAT, you need to have a small handle on what these things are. We will briefly, literally less than 10 minutes, talk about gluconeogenesis and glycogen metabolism. Those are things that you will break down in Biochem 2, but we're at least going to introduce those topics because they're really relevant. They really are relevant to glycolysis, the CA cycle, and the